Now discuss an all-important theory in thermodynamics called the kinetic theory of gases. Now, in this context, you must also appreciate how scientific theories evolve, how scientific theories take shape, how they are tested, how they stand the test of time, how they get modified, how experimental results are often used to test the theories, and so on. Now, what does kinetic theory deal with? Kinetic theory of gases is an attempt to describe how gases behave. Now, is it possible for us to go among the gas molecules to see exactly how they behave? You see, direct observation is very difficult. In fact, one of the first studies done to find the behavior of molecules was actually Brownian motion, the motion of molecules of liquids. Because you cannot really see molecules, you have to make a lot of assumptions. So, kinetic theory of gases, we don't know how molecules look like, but based on our observations in the large scale, we're going to depend on some intelligent assumptions that we make. And we're going to build a theory based on those assumptions. And the theory will yield some results which can then be tested. And depending on the results of the test, we can then decide, is the theory a good theory or a bad theory? If it is not a good theory, we need to come back and change our assumptions. You see, this is how scientific theories work. And these kind of assumptions we very often called hypotheses. So in this case, what do? We base our theory on certain, intelligent assumptions. Kinetic theory of gases make the following assumptions. Now look at the assumptions kinetic theory make. A gas is made up of identical spherical molecules which are in a state of random motion. And Newton's laws of motion can be applied to explain their motion. In other words, these molecules behave like any other objects. In other words, when they are subjected to forces, Newton's law of motion will apply to them. Now, what is the second law of motion? Anybody recall? Well, the second law of motion deals with the change in momentum of an object when subjected to a force. It says the rate of change of momentum is proportional to the force acting on the object. In fact, we defined unit force in such a way that force is a direct measure of the rate of change of momentum. We are going to use that in this class. So, rate of change of momentum is a measure of the force acting on a molecule. We assume that Newton's law of motion can be applied to the motion of these molecules. Assumption 2, the volume occupied by the molecules is very small when compared to the volume of the container. If you take a container like this, and if you squeeze all the molecules in here into a small space, that space will be very small compared to the total volume of the container. The volume of one molecule is so small compared to the volume of the container. Third assumption, the molecules undergo elastic collisions. What are elastic collisions? You recall the definition of elastic and inelastic collisions. You see, all collisions conserve momentum, but only elastic collisions conserve kinetic energy. So when the molecules collide, momentum is conserved, also kinetic energy is concerned. Molecules undergo elastic collisions with one another and also with the walls of the container. And the pressure exerted by a gas is actually due to the changes in momentum they impart on the walls of the container. They are hitting continuously on the walls of the container. Pressure exerted by a gas is due to the hitting of these molecules on the walls of the container. You remember we said at absolute zero, at 0 Kelvin, a gas ceased to have any pressure. Why? Because these molecules cease moving, and when they are not moving, they are not hitting the container. They are not exerting pressure. So pressure exerted by a gas is actually due to the collision of these molecules with the walls of the container. We are going to use that to derive an expression for pressure. We will use this assumption to derive an equation for pressure exerted by a gas. You see that? And then we can test that law using the gas law that we have discussed and also many other concepts that we know are true. And then we can test the validity of these assumptions. Assumption number 4. The forces between molecules are negligible except during collisions. In a gas, the molecules are absolutely free from each other's influence. There is virtually no intermolecular forces. You see, in a solid, intermolecular forces are great. In a liquid, again, the intermolecular forces are quite considerable. In a gas, the intermolecular forces are non-existent. In other words, the potential energy is a maximum. Is that right? They exert no force on each other. And our theory is going to be built on these assumptions. Well, we had actually looked at how gases behave when I showed you how temperature depends on the kinetic energy. Now here I have an illustration of the assumptions that we made. That the gas molecules are spherical and they are in a state of random motion. They hit against each other. They hit against the walls of the container. The volume occupied by one molecule is so small compared with the total volume that the space occupied by a molecule is very, very small. All right, what else did we say? We said these molecules interact in such a way that they hit against each other, but except at that time, they exert no force on each other. The intermolecular forces are virtually non-existent. And also I told you the pressure exerted by a gas is due to the hitting of these molecules. You can see they actually hit against the walls of the container. All right? Now, these are the assumptions on which we are going to base our theory. These assumptions we made, we will now use to obtain an expression for the pressure exerted by a gas. All right? Now, the figure shows a box containing a gas. Now here, this is the kind of box that we have, and this is the area A, and it contains a large number of molecules. And you must understand that the speed of these molecules, they are all moving at random. So there is no way you can look at a molecule and say, all right, this is going in the X direction. No, the speeds are distributed randomly. All right? Now, let there be n molecules. Let the total number of molecules in this box be n. And let the mass of each molecule be small m. So watch all these assumptions that we make. Now, we assume that the average velocity of a molecule is v bar. Now why do we have to say average velocity? Because not all molecules have the same velocity. They all have different velocities. The distribution of velocities will keep changing. So we will take for our purpose that there are a total of n molecules in the container. Each molecule has a mass m and has an average velocity v bar. Okay. Since the velocity is in any random direction, we assume that v sub x is the average x component of this velocity. You take a molecule, the velocity of a molecule can be at any random directions, but it has an x component, a y component, and a z component. So we are going to concentrate on the motion of this molecule in the x direction. And then we can take the y and z components later on, right? So let v sub x be the x component of this average velocity. All right, so you got a molecule there, its velocity is v sub x. If uppercase V is the volume of the box, the number of molecules per unit volume, what would that be? If the volume of this box is V, and how many molecules are contained in that volume? There are n molecules in that volume. Therefore, what is the number of molecules per unit volume? Will be n over V. N over V now represents the number of molecules per unit volume. Let A be the area of the side of the box on the right. This area, let this area be A. Just like the box I showed you, this area is A. That means we are now, since we are talking about the average x motion of the molecule, we are now going to say these molecules are moving towards that wall with that average x velocity. When the molecules have an elastic collision with this wall, they just reverse their velocities. We said the collisions are elastic. That means when they collide, they don't lose energy. So if a molecule comes towards the wall like this, they collide and move away with the same speed. They don't lose speed when they collide. Is that right? Now, like this. Okay. The momentum of a molecule in the x direction, if you have a molecule that has the velocity, look at this. This molecule has the velocity v sub x. Its momentum in the x direction is m times vx. Now, the momentum of the molecule after collision, as the molecule approaches the wall, its momentum is mvx. And after collision is going to move away. That means its momentum is now reversed. Its momentum after collision is negative mvx. Therefore, what is the change in momentum of the molecule? This is the initial momentum mvx. The final momentum is negative mvx. The change in momentum is mvx minus negative mvx. So we have delta px. What does delta px stand for? The change in the momentum, equal to 2 mvx. So every molecule that hits the wall of area A will experience this change in momentum, that is 2 mvx. There you are. You got mvx is the momentum as it collides. Negative mvx is the momentum after collision. The change in momentum will be 2 mvx. Suppose you consider a time interval delta t. All the molecules in a volume A Vx delta t will reach the area in that time. Do you understand that? You see, if this molecule has the velocity v, what does it mean? It means it will travel a distance v in 1 second. So from here, in 1 second, it will reach there. That means it travels the distance v. So if there are many molecules in this area, during that time, all those molecules would have reached the wall. So if you consider a time delta t, look at the volume AVX. What does AVX tell you? A is the volume of the box. Vx is the velocity of each molecule. So if this molecule is going to reach the wall in 1 second, that means all the molecules along with it and in front of it will also reach the wall during that time. So the volume, this is the volume A times Vx. See, this is the length Vx. In 1 second, all the molecules in the volume A times Vx will all reach that wall. And therefore, in a small interval delta t, the molecules in this volume A Vx delta t, all those molecules will reach the wall in that small time interval delta t. Alright, but at any given time, only half the number of molecules are likely to be moving to the right. The other half will be moving to the left. Therefore, we need to make an adjustment here. The number of molecules reaching area A in that time delta t will be 1/2 of this. 1/2 of A times Vx times delta t. And of course, this is the number of molecules per unit volume. So, if you multiply this with the number of molecules per unit volume, that will give you the total number of molecules reaching that wall, and only half of that will be likely to be moving to the right. The other half is moving to the left. So what does this quantity represent? This quantity represents the number of molecules that is likely to hit the area A during that time delta t. Now, the change in momentum of all these molecules, this is the number of molecules that reach this area A in that small time interval delta t. And each molecule suffers a change in momentum given by how much? Each molecule suffers a change in momentum mvx minus negative mvx, which is 2mvx. So if you now multiply this quantity with 2mvx, that will give you the total change in momentum experienced by all these molecules. So the total change in momentum experienced by all the molecules that reach this wall of area A in this time interval delta t is 1/2 n over v A Vx delta t. That is the number of molecules reaching the wall in that time, multiplied by the change in momentum of each molecule, that is 2mvx. What does that simplify to? Well, the 2 and the 2 goes, and Vx will multiply by Vx will give you Vx squared. That is n over v am Vx squared delta t. What does this represent? This represents the total change in momentum that happens at this wall during this time interval. Alright, So this is a measure of the total change in momentum during this time interval. Therefore, what is the rate of change of momentum of these molecules? The change in momentum divided by the time represents the rate of change of momentum. So delta px divided by delta t, that gives you n over v am vx squared is a measure of the rate of change of momentum. All right, what did we say Newton's second law is? The rate of change of momentum is a measure of the force exerted on the wall. According to the Newton's second law, this rate of change of momentum is a measure of the force exerted by these molecules on the wall, because the change in momentum happened because the molecules hit the wall. You see? So that rate of change of momentum is a measure of the force exerted by all these molecules on this wall. Therefore, we can say if Fx, we are now considering only the x direction. If F sub x is the force exerted on the area A by these molecules, we can say F sub x equal to n over v am vx squared. Well, now look at how a theory takes shape from mere assumptions. Don't you admire physicists and chemists who work and obtain these kind of beautiful relationships based on imaginations? All right, that's how science works. That's how science grows. And that's the reason why we say science never gives you the absolute truth. It gives you avenues to explore continuously. So all these theories are subject to questions, subject to change. That is the premise of science. That is how science works. The pressure exerted by the gas, therefore, the pressure exerted by a gas. You see, this is a measure of force. Force exerted by those number of molecules on this wall of area A. What is the definition of pressure? I hope you remember. Pressure is defined as force per unit area. So if you know the total force acting on a certain area, that force divided by area will give you the pressure. Pressure equal to force divided by area. So let's divide both sides of this equation by A. You can f of x divided by A will be n over v m vx squared. So pressure is force divided by A equal to n over v m vx squared. All right. There we have an expression for the pressure. But is that the final version? We have only considered the x motion. Well, from here, you know, cross multiply P times V equal to nm Vx squared. But you know that PV equal to NNAKT. You remember that one? PV equal to nRT, where R is Avogadro's number times Boltzmann constant, Na times K. So PV equal to N the number of moles, Na the Avogadro's number, K the Boltzmann constant times T. That is equal to N times Na, the number of moles multiplied by the number of molecules per mole, that N times Na is the total number of molecules. So what do we have now? We have PV equal to NKT, where N is the total number of molecules, K is the Boltzmann constant, T is the absolute temperature of the gas. So nkt equal to nmvx squared. How did I get this one? Look at this. PV equal to nmvx squared. That is what we have been working hard so far to obtain. And this is the result that we already know from ideal gas law. So ideal gas law tells you that PV equal to nkt. From our assumptions, we obtained PV equal to nmvx squared. So, if our assumptions are right, then this nkt must be equal to nmvx squared. Is that right? Okay. That means K times T equal to, that means N, the big N, the number of molecules on each side will cancel. We get K times T equal to mvx squared. That's an important relation. Now, if K times T equal to mvx squared, then 1/2 kt will be equal to 1/2 mvx squared. Why did I do that? Because we are so familiar with this quantity, 1/2 mv squared. 1/2 mv squared is a measure of the kinetic energy of a molecule. You see, Vx stands for the x velocity of the molecule. Mvx squared is the kinetic energy of the molecule moving in the x direction. So 1/2 mvx squared is a measure of the kinetic energy of a molecule moving in the x direction. And what is that equal to? Equal to 1/2 kt. The energy of a molecule in the x direction is 1/2 kt. I want you to remember that one. All right. Average kinetic energy due to the x motion equal to 1/2 kt. That means average energy due to y motion also will be 1/2 kt. Average motion due to z direction motion also will be 1/2 kt. That means average energy due to each type of motion, x motion, y motion, z motion. Each of these motions will give an energy of 1/2 kt. But the molecule is equally likely to move in the x, y, and z directions. Therefore, Vx squared can be approximated as 1/3 of the square of the actual velocity. You see, this Vx squared, if the velocity of this molecule is in any arbitrary directions, it is made up of Vx, Vy, and Vz. Therefore, we can consider this Vx squared as 1/3 of the square of the average velocity of the molecule. So how do we write that? If V bar is the average velocity of the molecule, you remember we started with that assumption. V bar, V with a line on top is V bar, is the average velocity of the molecule, then this Vx squared, that is the velocity in the x direction, is 1/3 of that V bar squared. Does that assumption make sense? I think so. So, this Vx squared can be now replaced as 1/3 V bar squared. The average kinetic energy of a molecule, therefore, is given by K average is 1/2 mv bar squared. This is the average kinetic energy of a molecule, where V bar is its average velocity. Now, I'm going to replace this V bar squared. Look at this. This V bar squared is replaced by 3Vx squared. Because we said Vx squared is 1/3 of V bar squared. V bar squared, therefore, is 3 times Vx squared. So the average kinetic energy of a molecule is 3/2 3 over 2. Well, let me write that step for you. I omitted a step there. What that means is it will be 1/2 times m times 3v squared. That will be, you see, this 3 I'm going to write as 3 over 2 mvx squared. Is it all right? 3 over 2, this is the 3 over 2 mvx squared. But what does mvx squared equal to? If you remember, if you simply take away these 1/2, this mvx squared equal to kt. So I can therefore say this is equal to 3 over 2 mvx squared, which is 3 over 2 kt. Now look at that. The average kinetic energy of a molecule is 3 over 2 kt. I want you to sort of assimilate that information. Now, this 3 over 2 kt is actually made up of 1/2 kt along the x direction, 1/2 kt along the y direction, and 1/2 kt along the z direction. Now, we assume that a molecule is free to move in the x, y, and z directions. And we say a molecule has 3 degrees of freedom. What is the meaning of a degree of freedom? The freedom of a molecule to move in a direction. It can move in the x direction, y direction, and z direction. So we assign 3 degrees of freedom. The energy of a molecule in the x direction we calculated as 1/2 kt. The energy of the molecule in the y direction is also 1/2 kt. The energy in the z direction is also 1/2 kt. So the total energy of a molecule, the average kinetic energy of a molecule, is 3 times 1/2 kt, 3 over 2 kt. So if I ask you, what is the kinetic energy of a molecule per degree of freedom? What would be the answer? Per degree of freedom. This is the total kinetic energy for 3 degrees of freedom. Therefore, the energy of a molecule per degree of freedom is 1/2 kt. Don't forget that. I will ask you that about 2 classes from now. The energy of a molecule per degree of freedom is 1/2 kt, where K is Boltzmann constant and T is the absolute temperature. The total translational kinetic energy of n moles of a gas containing n molecules. This is the total energy, translational kinetic energy of 1 molecule. So what is the total kinetic energy of n molecules? That will be, the total kinetic energy is 3 over 2 n kt. That will be 3 over 2 n RT. Did you understand how nk become nr? I hope you understand that. Let me show that to you. Now, take this n times k. The total number of molecules can be written as Na times n, and that is multiplied by k. I hope you understand that. The total number of molecules is the number of molecules per mole, that is Na, that is Avogadro's number, multiplied by the number of moles. This will be your n. And you know, Na times k, what do you call that? Na times k is called your R. So big N times k equal to small n, the number of moles, times Na times k is R. Okay, let's go on. So 3 over 2 nkt is the total translational kinetic energy of n molecules, which is the same as 3 over 2 nRT. Alright? If m total is the mass of n molecules, m total simply is a notation we use for the total mass of n molecules. What is the mass of one molecule we assumed earlier? The mass of one molecule we assumed as lowercase m. Therefore, what is the mass of n molecules? That will be n times m. So, if m total is the mass of n molecules, then 1/2 m total V bar squared. Remember here, this K stands for the total kinetic energy of n molecules. And this n molecules has this mass, the total mass of n molecules. And you know that kinetic energy is 1/2 mv squared. M is the total mass of these n molecules. V bar is the average velocity of each of those molecules. Therefore, 1/2 mv bar squared is a measure of the total kinetic energy of all those molecules. And that should be equal to 3 over 2 nRT. Now, look at this. I consider this as a beautiful equation. It is going to lead us to the average velocity of a molecule. We can now measure the average velocity of a molecule. Isn't that beautiful? Yes. We get V bar squared equal to 3 nRT over m total, or that will be 3 RT over, what I did is, this n, I divided this by that n. Do you understand that little manipulation? You see, m total divided by n. This n actually belongs to the numerator. But if I write it like this, it has a significance. What is the significance? M total divided by n. Tell me, what does that represent? The total mass of the gas divided by the number of moles of that gas is the molar mass of the gas, the mass of 1 mole. So this will be 3 RT divided by m, where m is the molar mass. V bar squared equal to 3 RT over m, where m is the molar mass. What is V bar therefore? V bar therefore is square root of 3 RT over m. Isn't that beautiful? We can calculate the mean velocity of a molecule. Now, V bar is called the root mean square velocity of the molecule. So the root mean square velocity, you simply understand it as the average velocity of a molecule is square root of 3 RT over m. And we also very often call it VRMS. RMS stands for root mean square velocity. So VRMS equal to square root of 3 RT divided by m, where R is the universal gas constant, T is the Kelvin temperature, m is the molar mass. You can see R is a constant, the molar mass of a substance is a constant. Therefore, what does the velocity depend on? On the temperature. That means temperature, do you remember in the earlier part of this lesson we said temperature is proportional to the average kinetic energy of the molecules. You see that? And that's what this relation tells you. 3 over nR is a constant. So the kinetic energy is proportional to the temperature. You can see our assumptions are proving to be so good. Alright, now we are ready to use this to solve a couple of problems. Problems using the results we obtained so far. Find the total translational kinetic energy of 1 liter of oxygen gas held at a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. What is the RMS speed of the oxygen molecule at this temperature? You have two things to calculate. Let's pick our data. The volume of the gas is 1 liter, and convert that to meter cube. That will be 10 to the power of -3 meter cube. Is that right? 1 liter is 1,000th of a meter cube. The temperature is 0 degrees Celsius, 273 Kelvin. Pressure is 1 atmosphere. We are using all absolute units. Volume in meter cube, pressure in Pascal. 1 atmosphere is 1.01 times 10 to the 5 Pascal. The total translational kinetic energy of n moles of a gas. Do you remember that equation we just got 2 slides ago? The total translational kinetic energy of n moles of a gas is 3/2 nRT. Is that right? Yes. So this is the total translational kinetic energy, which is 3/2 nRT. If you remember, we had it earlier as 3/2 uppercase NKT, which is the same as 3/2 nRT. Well, we need to find the value of this. Is there any way we can do this? Do we know N, the number of moles? Well, of course we know R. When volume is measured in meter cube and the pressure in Pascal, the value of N is 8.314 joules per mole per Kelvin. Well, because we don't know N, we are going to take another route. You know, NR or nRT. What is the universal gas law? PV equal to nRT. Is that right? So you can see I colored nRT red because I can replace that nRT now by PV. Why? I know the pressure, I know the volume, therefore this is a much easier route for us to take. The total translational kinetic energy of the n moles of gas is 3/2 PV. Now, put in the values of P. P is 1 atmosphere, 1.01 times 10 to the 5 Pascal. And the volume is 10 to the -3 meter cube. That gives you K as 151.5 joules. You see, in order to get K in joules, you need to have the volume in meter cube and the pressure in Pascal. So you need to use the absolute unit. Alright, we now need to find the RMS speed of oxygen molecule. Now what's the equation for RMS speed of a molecule? V RMS is square root of 3RT over the molar mass. That means you need the molar mass. What is the molar mass of oxygen? The molar mass of oxygen is 32 grams. The molecular weight of oxygen is 32. The atomic weight is 16. But oxygen is a diatomic gas. That means its molecule is made up of 2 atoms. So the molecular weight of oxygen is 32. That means the mass of 1 mole of oxygen is 32 grams, which is 0.032 kilogram. V RMS is square root of 3RT over the molar mass. We know the value of R, we know the value of T, and now you know the value of M. Therefore, using all those values, we get V RMS is 461.3 meter per second. At 0 degrees Celsius, the oxygen molecules have an average speed of 461.3 meters per second. It's an enormous speed. All right, let's do another problem. In a period of 1 second, 5 times 10 to the 23 nitrogen molecules strike the wall with an area of 8 centimeters squared. If the average velocity of the molecules is 300 meters per second and strike the wall head-on in a perfectly elastic collision, what is the pressure exerted on the wall? The mass of nitrogen molecules is 4.68 times 10 to the negative 28 kilogram. All right, let's pick the values that are given. And the total number of molecules are given to us, 5 times 10 to the 23. The average velocity of a molecule is given to us, is 300 meters per second. The mass of a molecule is given to us, that is 4.68 times 10 to the negative 28 kilogram. The area on which these molecules collide is A equal to 8 times 10 to the negative 4 meters squared. What do we need to find? We need to find the pressure exerted on the wall. Well, first we find the total force. The change in momentum of one molecule due to collision. You remember we said we obtained that as 2mvx. mvx is the momentum forward. It collides and rebounds with a momentum negative mvx. Therefore, the change in momentum is mvx minus negative mvx is 2mvx. That will be 2 times mass of one molecule multiplied by the speed, the average speed of that molecule. That is 2.81 times 10 to the negative 25 Newton second is the change in momentum of one molecule. And how many molecules are there? Well, there are these many molecules. Therefore, the change in momentum of these many molecules, 5 times 10 to the 23 molecules, is multiply the change in momentum of one molecule with the total number of molecules, and that will give you delta P. The total change in momentum is 0.1404 Newton second. All right, the rate of change of momentum is, this change in momentum occurred during a time 1 second. So the rate of change of momentum is delta P divided by delta T. Delta P is this, and delta T is 1 second. Therefore, the rate of change of momentum is 0.1404 Newton. And what does rate of change of momentum represent? The rate of change of momentum is a measure of the force. So, this is a measure of the force F acting on the wall due to the collision, because the change in momentum is due to the collision. So that change in momentum is a measure of the force exerted by the molecules on the wall. So what is the force exerted on the wall? This is the force exerted on the wall. Pressure is force per unit area. So divide this force by the area of the wall. That will be 0.1404 Newton divided by 8 times 10 to the negative 4 meters squared. That gives you 175.5 Newton per meter squared is the pressure exerted on the wall. And you know Newton per meter squared is a Pascal. Okay, now these problems are representative problems and you must be familiar in doing this. Let's do another problem. at what temperature will the RMS speed of a hydrogen molecule equal to 331 meter per second? Well, the information you have, hydrogen. Now, what is the molar mass of hydrogen? You have any idea? Well, if you look at the periodic table, it will give you that value. The RMS speed is given to us is 331 meter per second. We need to find the temperature. Vrms is square root of 3RT over M. And what is therefore temperature? The temperature solved for T, square both sides. Vrms squared equal to 3RT over M. Therefore T equal to Vrms squared times M divided by 3R. You know the value of R. Do you know the value of M, the molar mass of hydrogen? The molecular weight of hydrogen is 2. That means the molar mass is 2 grams per mole, which is 0.002 kilogram per mole. So, using the values of Vrms, the molar mass of hydrogen, and the value of R, we can now calculate the temperature. The temperature is 331 squared times 0.002 all over 3 times H.314, and that is H.79 Kelvin. You can see we have a large amount of information about the gases. Now you can calculate. Now you remember that the theoretical formulations we did in this class is based on assumptions, and we will be now testing these assumptions as we go on. Now, if the results that we obtained, that, for example, this is the results that we obtained from our assumptions about the behavior of gas molecules. Now, when you test it, if you can measure the actual speed of molecules, and if the equation can stand that test, then our assumptions are right. But sometimes we may have to go back and revisit our assumptions and make changes to it. We will see as we go on. Alright, I'm going to stop this lesson here. I will get back to you with another lesson on thermodynamics a little later.